Welcome, everyone. Thank you for joining us for today's webinar, Optimization Study of Supercritical Fluid Extraction of Cannabinoids from Cannabis Sativa, presented by Eric Kawka, founder of Cattis Scientific. My name is Xavier Gutierrez, and I will be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots. LabRoots is the leading scientific social networking website and producer of educational virtual events and webinars. Now, before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want during the presentation. Simply click on the Ask a Question box located on the far left of your screen and type your questions into the drop-down box. Our speaker will respond to your questions via email following the presentation. And if you have trouble seeing or hearing the presentation, please click on the Ask a Question box to let us know that you're experiencing a problem. And this presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located in the top right corner of the presentation window and follow the process to obtain your credits. Now, without further ado, please join me in welcoming Eric Kawka. I will now turn the presentation over to him.
Hello, my name is Eric Kawka. I'm the founder of Cattis Scientific. We're a R&D laboratory in Hardwick, Vermont. Hardwick is the northeast corner of Vermont, almost on the border of Canada. And we focus our efforts on exploring SFX technology and how that relates to cannabis. And when I say SFX, I'm referring to SFE, supercritical fluid extraction on the front end, and also both preparative and analytical SFC, supercritical fluid chromatography, on the back end. And so today we have a few slides outlining some optimization work that we've been doing using supercritical fluid extraction techniques targeting cannabinoids from industrial hemp. And so before we get into the slides, let's appreciate the complexity of cannabis. And within cannabis, we're really interested in two classes of compounds. One class are terpenoids. And terpenoids are the natural aroma and flavor molecules of cannabis. And in nature, we've identified around 3,000 different terpenes. Of these 3,000 terpenes, the cannabis plant makes or we identified of these 3,200 within cannabis. Another class of compounds that we're really interested in are cannabinoids, THC, CBD, CBG. There's 80 plus cannabinoids that we have identified in cannabis. And of course, a lot of those cannabinoids are minor cannabinoids. And the two classes of compounds, cannabinoids and terpenoids, together give us this entourage effect. And Ethan Russo best describes that entourage effect, where he says, the idea of 2 + 2, instead of that equaling 4, it'll yield 8 in medicinal value. And so these terpenoids and cannabinoids, they interact within our endocannabinoid system. And within our endocannabinoid system, we have around 300 different receptors. And each receptor can accept multiple terpenoids and multiple cannabinoids. And so if we were to ask the question, how does cannabis work? Well, that's a really complex question, right? And we really can't take a monopharmaceutical approach to that question. Of course, monopharmaceutical being one compound for one condition. Instead, we take a polypharmaceutical approach where we have multiple components interacting together. And so kind of to recap really quick, there's 200 plus terpenoids, 100 plus cannabinoids interacting on 300 different receptors, where each receptor can accept multiple cannabinoids and multiple terpenoids. So as you can imagine, to answer a simple question, how does cannabis work? Well, that becomes a very complex problem to solve. And so here we have what I like to call my California cruiser. In this slide, it's a work in progress, and it's an attempt to explain the relationship between terpenes and cannabinoids. And the way I like to explain it is a bicycle. And a bike has two wheels, a front wheel and a back wheel. And we know that the back wheel of a bike provides the energy to propel that bike forward, while the front wheel kind of steers the bike. And now what I like to do is imagine the back wheel being cannabinoids in cannabis, propelling, fueling that euphoric psychoactivity, while the front wheel are terpenoids, kind of altering the direction of how we're going to feel from that particular strain of cannabis, right? And so basically, you know, on one side, indica, which more sedative type properties, on the other side, sativa. Once again, it's still a work in progress, but we'll just leave that there. So today we have a few slides. We'll start by reviewing some prior work done on extracting cannabinoids from cannabis utilizing supercritical fluid extraction. Then we'll extend the boundaries of cannabinoid extraction utilizing CO2 by looking at the mass transfer property of CO2. And of course, mass transfer being the flow rate of CO2. And then we'll have a quick slide on future optimization work that we can do. So if you were to Google supercritical fluid extraction and natural products, and you'll probably get 1,000+ different hits on Google. And this is one example, a publication from 2011, where this group explored extracting sugar cane and cloves utilizing SFE. And they built these overall extraction curves, where on the x-axis we have time, on the y-axis we have percent of our COI, compound of interest. And their goal was to develop these overall extraction curves, and from that data, develop a strategy to scale from 250 ml vessel to a 5-liter vessel. And they were able to do this by maintaining their solvent to feed ratio, S/F. And we'll talk more about that in the later slides. And if you were to refine your Google search, and if you were to search SFE and cannabinoids, well, from 1,000 hits, we get a very limited number of publications. And this is one of the first publications that came out in 2010, where this group looked at the solubility of cannabinoids in supercritical CO2. And of course, solubility data is super important. If we know the relative solubility of terpenes in CO2 and the relative solubility of cannabinoids in CO2, well, then we could effectively remove these two classes of compounds from each other. And within the class of terpenoids, once again, if we know the solubility data of terpenes within the class of monoterpenes and sesquiterpenes, well, by utilizing SFE, we're able to separate our monoterpenes out from our sesquiterpenes. Also, on the cannabinoid side, with the proper solubility data, we're able to separate our acidic cannabinoids from our neutral cannabinoids. And so from this work, we know that CBD is way more soluble in CO2 than CBDA. CBDA is more soluble than THCA, and also THC is more soluble than THCA. Another publication that you'll find online is from 2017, where this group investigated extraction of SFE, but looking at different co-solvents and different strategies of introducing that co-solvent into the extraction chamber. And so they looked at two strategies. One is a constant flow of ethanol, meaning that they're just throughout the life of the extraction, they're flowing in a constant X ml of ethanol. And the second strategy was a pulse strategy of ethanol, where they will pulse X amount of ethanol at different various stages of the extraction. And what they concluded is a pulse strategy is more effective than a constant flow. And with the pulse flow strategy, they were obtaining extraction efficiencies of 92% and higher. And so terpenoids and cannabinoids are synthesized and stored within the trichome. And the trichome is this glandular hair-like structure, as pictured here. And depending how we separate or concentrate that trichome, well, that will dictate what kind of product we make. right? And so kind of two different approaches. We can make ice water hash, where we're just knocking off that trichome and sifting it through to make a concentrated product, or we could selectively extract that trichome utilizing CO2, and both will yield different products. In terms of CO2 and utilizing SFE, the way we prepare the material will dictate how efficient our extraction will be. And we'll see a little bit more on that on the next slide. And so here we have an efficiency curve, a CO2 efficiency curve. And so if you were to graph out your extraction, where we have time on the x-axis and grams of COI, compound of interest, and in this example, it's CBD from hemp, on the y-axis, you'll see a graph that looks something like this. And there's two evident regions within this curve that we'll see. And the first region, I like to call the mechanical region. And then the second region is the diffusion limited region. And so within the mechanical region, folks that have experience utilizing SFE, using SFE for extraction, you'll notice that within the first 60 minutes, you get a rush of material, right? And so why does that happen? Well, it goes back to how you prepare that material. And so first, you probably ground that material. And when we grind cannabis, right, we're knocking off those trichomes. And during our mechanical region of extraction, those trichomes are liberated from the flower, and they're available for the CO2 to basically pick it up and transport it into our extraction vessel, right? After the mechanical region, the extraction gets a little bit tougher, and we enter the diffusion limited region, where solubility really has to happen. The CO2 has to come in, has to cleave that trichome, and then once it cleaves the trichome, it's able to transport the contents of that trichome from the flower into our collection chamber. And so the mechanical region happens pretty fast. The diffusion limited region is kind of the painful region of extraction. And so this work, we're looking at how can we make the diffusion limited region less painful? How can we expedite that process in SFE? And so we have three parameters that we can control utilizing CO2. And the first two parameters are thermodynamic properties, pressure and temperature. And at a specific temperature and a specific pressure, we could calculate a density. And based off that density number, typically the higher the density, the more aggressive CO2 will be. And the lower that number, the less aggressive CO2 will be in terms of extraction. And the third property is mass transfer, flow rate. And typically, one would think the higher the flow rate, well, the higher our rate of extraction is. And the lower the flow rate, well, the lower our rate of extraction would be. And I have question marks on the graph here. And the reason being is I do believe that that is true when we're speaking in terms of the mechanical region of the extraction curve. And so the more CO2 we flow through the mechanical region, the faster that we'll extract that region. However, when we enter the diffusion limited region of the extraction curve, I'm not convinced that a higher flow rate means a faster extraction. And we'll see why in the slides to come. So a lot of times I like to explain something complicated, like extracting cannabinoids from cannabis, and explain that in terms of something that we do every day. And for me, it's brewing a cup of coffee. And so kind of looking at the workflow of brewing coffee, right? And, first it starts with selecting the right bean. And of course, we know that a coffee bean from Costa Rica is completely different in flavor than, say, a coffee bean from Colombia. So next we locate our bean, and then we grind that bean, right, to make more surface area. And then if we're brewing some French press coffee, we load it into our extraction chamber. We fill that extraction chamber with our solvent. In this case, it's hot water. And we let that soak. Say we let that soak for 4 minutes. And while our coffee is soaking in the water, we're effectively extracting our compounds of interest. That may be the essential oils or caffeine, right? We're extracting without flow. We're letting solubility occur. After 4 minutes, we plunge that coffee and we harvest our extract with flow, and we pour it into our cup, into our coffee cup, and we effectively have a cup of coffee. Now, if we were to analyze this, the first round we do this, say we extract 10% of the available caffeine. And I'm just making 10% up for this example. Well, you can imagine we do this round again, right? So we take the extracted coffee from round one, we put it back into our French press extraction vessel, we fill water again, we extract without flow, we're letting solubility happen, we plunge the coffee, we pour it out into our cup, and then after the second round, maybe we extract an additional 5% of caffeine. And we can keep doing this over and over again until we effectively remove, say, 70% of the available caffeine. So that's one strategy of brewing coffee. The other strategy is, well, let's pack this coffee into a column and just blast water through it really quick, say at 100 liters per minute, right? And after 1 minute, we probably won't extract a lot of caffeine. Reason being, if we're flowing that water at a really high flow, well, we're not allowing solubility to occur, right? There's no time for the water to interact with the coffee. And so that would be not as an effective method as the first strategy, where we're allowing water to soak with the coffee and we're harvesting after soaking. And so this is the approach we're going to take with extracting cannabis. And I call it a static dynamic approach to boost efficiency in the diffusion limited region of the extraction, the efficiency curve. And we'll see how that plays out in the next slide or two. And so some of the instrumentation used for this work, the Waters bio-botanical extractor, a great piece of equipment for this work, because we have control at each point. We were able to control our flow rate, we're able to control the temperature at each zone, and also we're able to control our pressure. And on the analytical side, we're using a QD UPC squared. So this is our experimental setup. So in Vermont, we have a very limited medical marijuana program. However, hemp is pretty open. And so our laboratory does all our work on industrial hemp. And so for this work, we've acquired 25 pounds of high CBD hemp. We homogenized all 25 pounds, and then we tested it to get 13.5% CBDA. And we're running 3 different trials. Trial 1, we're extracting at 250 bar at 50 C, and this is a dynamic run. So basically, we're flowing at 200 grams per minute for 550 minutes. Condition set number 2, we're extracting at 250 bar at 50 C, and now we're taking a dynamic static approach. We're extracting for 60 minutes, and then we're soaking for 15 minutes. We're extracting for 60 minutes, soaking for 50 minutes. And we keep doing this on and off for a total of 550 minutes. So we're keeping the time constant here. That's trial number 1. And then trial number 3, we're extracting once again at 250 bar, 50 C. And we're also taking a static dynamic approach. But now we're keeping our solvent to feed ratio constant as trial 1. And when I say solvent to feed, I mean the ratio of grams of solvent used over grams of starting material. And that ratio is constant as trial 1. And so let's look at some data. Oh, so first is looking at the program of how the difference between dynamic and dynamic static. So on the top, really simple, we're just flowing at 200 grams per minute, and we're extracting at 250 bar, 500 for 550 minutes. And then in the dynamic static approach, we're altering our flow rate between 200 grams per minute and 5 grams per minute. So when we're extracting at 200 grams per minute, that's the dynamic leg of the run. And then when we reduce our flow to 5 grams per minute, we're calling that a static soak. Yes, we're flowing some CO2, but at 5 grams per minute, it's essentially just soaking there. And then all the way to the right, you can see we're extracting at 250 bar, and we're alternating 60 minutes at flowing at 200, and then we're reducing that for 15 minutes at 500, and we keep doing that. And so here's some data. And so in trial number 1, and this is the dynamic run, we've calculated the total potential CBD. And when I say total potential, I'm referring to 0.877 times CBDA plus the CBD number. And in trial 1, we have a total potential of 215 grams. We're extracting for 540 minutes. And we, at the end of the extraction, we harvested 148 grams. And so that gives us an extraction efficiency of 69%. And some other parameters that we're looking at here is how many grams of CO2 we used. We're looking at the S to F ratio, once again, grams of CO2 over grams of starting material. And then the next column, we're looking at how many grams of CO2 did we use per gram, extracted gram of CBD, right? And that's an important metric, which tells us how efficient are we using our CO2. So in trial number 2, where we took a dynamic static approach, where we were holding the time constant as number 1. And so once again, in the starting material, we've calculated that we had 223 grams of total potential CBD. Since we're keeping our time constant, we're extracting for 540 minutes. We harvested 124 grams of total CBD, which gives us a ratio or extraction efficiency of 56%. And so after trial 1, the initial thought was, we're not moving in the right direction of this optimization work. And this experiment's not working, right? 56 is definitely lower than 69%. But then when you look at the gram of CO2 per gram of CBD ratio, we went from 731 in trial 1 to 608 on trial 2. And so what that's telling us is, well, we're using our CO2 more efficiently, meaning we're pulling out more CBD per gram of CO2. So 2 conclusions. 1, we're not fully optimized here. However, we are moving in the right direction, right? And so quickly looking at trial 3, where now we took the same approach, a static dynamic approach, but now we're keeping our solvent to feed ratio constant, right? So effectively we're using more CO2. So we've calculated that we used 216 grams, or we had available to us 216 grams of CBD available. Now we're extracting for 650 minutes. Reason being, we're soaking for 15 minutes. After every dynamic run, we're soaking for 15 minutes. So that's accruing some time. But in trial 3, we harvested 191 grams of CBD, giving us an extraction efficiency of 88%. And looking at the other parameters, we've maintained our solvent to feed ratio of 59, which is great. And our grams of CO2 per gram of CBD is down to 572. Once again, meaning we're even more effectively using 1 gram of CO2 to pull out even more CBD, which is great. And so now our optimization work is moving in the right direction. We've boosted our efficiency from 69% to 88%. One little drawback here is our extraction time went from 540 minutes to 650 minutes. So our overall extraction is a little bit longer, but in a slide coming, we'll present a situation where we're able to maintain our 88% extraction efficiency, but also maintain our 540 minute extraction. So here we're looking at the raffinate. And so trial 1 is going from left to right on the diagram. 1 is from the dynamic run, and 3 is from the dynamic static, where we kept our ratio constant. And we're looking at, we're trying to gather some channeling data, and basically where is our CBD caught up in our extraction. And so if you imagine a extraction chamber, we take a sample from the bottom, from the middle, and from the top. And in the dynamic run, we've calculated that we're leaving behind 2.73% of CBD all the way on the top of the vessel. And on the bottom of the vessel, we're leaving behind 1.03% of CBD. In trial 2, where the conditions were not optimized, we left behind 4% CBD and 0.8% on the bottom of the vessel. And this was another indication where we were moving in the right direction with our optimization, right? Comparing, 1 to 2, in trial 1, we had almost 1% of CBD on the bottom. In trial 2, where we're not fully optimized, we only had 0.8% CBD. So that, once again, was telling us that we're using our CO2 more effectively. And then trial 3, where we were fully optimized, we left behind 1% on the top, 0.6% on the bottom, and that averages out to overall around 0.84% left behind in the raffinate. And so here are some chromatograms. It wouldn't be a presentation without looking at chromatograms. And so this is the raffinate. And on the top, we have the dynamic run, where we see some acidic cannabinoids left behind. In the middle, we have the dynamic static trial, where we kept the time constant. And we have some neutral cannabinoids showing up in there. And that's telling us that, yeah, we didn't pull out all the material. Even our neutral cannabinoids are left behind in our raffinate. And then down below, where we kept our solvent to feed ratio constant, we have little CBD, but or below the limit of detection on the THC. So that was the fully optimized run. And so looking at some extraction economics, we went ahead and calculated how many grams of total potential CBD are we leaving behind in the raffinate. And so in the dynamic run, we left behind around 67 grams of CBD. In the dynamic static run, we left behind, where we kept the time constant, we left behind 99 grams of CBD. Once again, that was not fully optimized. And then in the trial where we kept the solvent to feed ratio constant, we're leaving behind 25 grams of CBD. Now in our lab, we're defining 90% extraction efficiency acceptable. And so if we're normalizing all this to 90% extraction efficiency, and we're assigning a dollar value of how much grams of CO2 of CBD we're leaving behind, in Vermont, full spectrum CBD runs like around $35 a gram. And so on the dynamic run, we're leaving behind approximately $1,500. $1,500 we're losing per run. And so if we extrapolated this, for per week, where we did 2 extractions per day, so 10 liters a day, and we're leaving behind $1,500 each extraction, well, that's almost $15,000 a week that we're losing in CBD. And so if we left our optimization work right here, right? Even though, if you recall, we are extending a little time. We're adding an additional 110 minutes to our extraction. However, it's still worth it right now. We're saving $1,500 or $15,000 per week. But we went ahead and we further optimized this, that we'll see in the next slide right here. And so the next step was, previously we were just extracting for 60 minutes, soaking for 15. And those two numbers, 60 and 15, we just kind of came up randomly. And so next we wanted to see, well, is 60 and 15 the right numbers? Is 60 the right number to extract dynamically? Is 15 the right number to soak? And so for a few extractions, we tracked the extraction by collecting a sample every 15 minutes. And after 60 minutes, we let that soak for 15 minutes. And then during the dynamic run, we collected, once again, samples every 15 minutes. And if we looked at the upper curve at plot B, where we're looking at grams of, it's a rate, grams of CBD over time, we could immediately identify where our mechanical region of the extraction curve happens. And that is, within the first, in this case, within the first 60 minutes, we're just, we're cranking at 12 grams of CBD per minute. And so that's the mechanical region of the curve. And then the extraction dies down to the diffusion limited region. And so our next strategy was identifying, okay, let's identify how long the mechanical region lasts. And after that mechanical region, let's start soaking after that. And so we're from this graph, we're seeing that our extraction efficiency kind of levels out after 105 minutes. And then after 105 minutes, we'll start soaking for 15 and then extraction for 16. So what we're trying to do is save up our soak tokens and apply them to the back end of the extraction where we really need them during the diffusion limited region of the curve. And so now our program looks something like this, where we're dynamically extracting for 105 minutes at 200 grams per minute. And then after 105 minutes, we reduce our flow down to 5 grams per minute. And now we're starting our soak for 15 minutes, and we're going on and off, 1560, 1560. And so by saving our quote unquote, soak tokens for later in the extraction with this method, we are consistently obtaining extraction efficiencies, 90% and above. And once again, we're still maintaining our solvent to feed ratio of 59. However, so our efficiency went up a little bit more, but we're still extracting for 650 minutes. And so the next slide right here is, well, how can we maintain our 90% extraction efficiency, but complete the extraction in 540 minutes? And so this method becomes fully optimized when we're using 2 5-liter vessels. And so you can imagine a scenario where we have 2 extraction vessels, where we're extracting extraction vessel number 1 while we're soaking extraction vessel number 2. And so after extracting vessel 1 for 60 minutes, we switch. And so now vessel 1 is soaking while we're extracting vessel number 2. And we keep switching, that we keep doing this for 540 minutes. So now effectively, we're not losing that 15 minutes of soak time. We're just continuously extracting, but now we're altering the flow to different extraction vessels. And now with this tactic, we're able to maintain our 90% extraction efficiency, but also maintain our 540-minute extraction time. And so overall, we're witnessing a 30% boost in efficiency with the static dynamic approach when we apply that to the diffusion limited region of the extraction curve. I'd like to thank Andy Aubin from Waters Corporation, Sean Hellmuller from Deutsche Process Dr. John McKay from Synergistic Tech Associates for collaborating and bouncing ideas, and also LabRoots for putting this great event together. And of course, everybody that tuned in and is listening to this presentation. That's my story. I'm sticking to it. Thank you very much.
Well, thank you, Eric, for your informative presentation. I would also like to thank LabRoots for making today's educational webcast possible. And as a final reminder, our speaker will follow up with any questions you've submitted via email. That's all for now. Thank you for joining us, and we hope to see you again soon. Goodbye.